like rainbow eyes.
I have rainbow eyes.
I had a 99. What is it?
Probably died.
Yeah, I have no idea.
Rank in angle and
If you have rainbow eyes, I think you're awesome.
We'll begin with part C. Probably
If you have rainbow eyes, you get any.
I got a
Rainbow eyes?
You get rainbow eyes.
That would have like, your eyes are nice and then the rest. Doesn't matter, just the rainbow.
What if you had
Is that
rainbow
yours now?
eyes and green skin?
No.
And you were like really
Guess
fat.
what? I got a new
What
pen.
if you had rainbow eyes and green skin and you were really
They
fat?
want to like,
Sweaty.
focus like.
Then you would have
You had green skin.
like goblins and stuff.
Okay.
Oh, okay, fine.
Rainbow eyes are somewhat plausible. A human goblin.
With like the long ears and the green skin, like eating potato chips all day. Like, you know, sweating.
Man.
The flour, almond flour, oh, it tastes great. And I think that it's almond. I look for it.
You're a reptile.
No, yeah. Vegan doesn't mean vegan.
Is Spider-Man? What is Spider-Man?
All right. So if you recall, I know it was a couple of days ago at the end of class last time, I had done parts A and B of a series of problems involving a one-dimensional elastic collision. In the first two examples, the objects were of equal mass, and the end result is that in such a situation, the objects just exchange velocities. Now in part A of this original example, we began with two parts of equal mass, so one of the objects was initially at rest, and then this object over here was initially moving in this direction with some speed. And then after the collision, this object here ended up at rest, and this object ended up here with the same speed as that of this one originally. In other words, the objects just exchanged velocities. Same thing happened in part B of the problem, where the objects just bounced off each other in some manner like so. And as they did, once again, because the masses are equal, the objects just exchange velocities. That always happens when the objects are of equal mass, they just exchange their velocities. However, if they are of different mass, just to finish off the one-dimensional collisions in this manner with this example, nothing relatively interesting happens. You just have to slog through the algebra and then calculate out whatever it is that we have to find. So let's go ahead and finish the one-dimensional elastic collision with this part C. And then, of course, I'll demo it after we plow through it. So one of the objects has a mass of 1 kilogram. It's initially moving to the right-hand side at 3 meters per second. And then it overtakes the second object, so the second object's moving initially in the same direction. The second object is more massive, mass of 2 kilograms, and it's moving initially with a speed of just 1 meter per second. The objects will bounce off each other in some manner, and then we find the final velocities of each. Okay, so basically what we do is set up our expressions. I'll do so in symbol form first. And then in order to make the problem as easy on ourselves as we possibly can, then you just immediately start plugging in your numbers and then solve for the two final velocities. So here's then what this begins to look like. So first of all, we have object now, I'll call it M1, equal to 1 kilogram, with an initial velocity vector of V1 to the right-hand side at 3 meters per second. Okay, then we have our second object here, M2, equal to 2 kilograms. This object is initially also moving to the right-hand side, but with a velocity V2 naught that's just equal to 1 meter per second. The objects collide, bounce off each other in some manner, and then intuitively we don't know whether or not, for example, M1 continues in this direction of motion or it rebounds. We don't know. So M1 is going to have some final velocity we have to find, V1 final. And then object M2 presumably keeps going in its original direction of motion, like so, with a V2 final, which is once again our unknown. And now we just set up our two expressions. So the first expression is conservation of momentum first, So we're going to have change in momentum of number 1 plus change in momentum of number 2 is equal to 0. And now we just start filling in all of our terms. So first of all, with just the symbols themselves, for object number 1 first, we're going to have its final momentum, m1 v1 final, minus its initial, m1 v1 naught. So that's our first term. And then for object number 2, we have its final momentum, m2 v2 final, minus its initial, m2 v2 naught. Like so. And then just in simple form here, notice that nothing cancels out. Because nothing cancels out here, if we kept everything in terms of the symbols, then it's a huge algebraic mess. We don't want to do that. We want to make the process as easy on ourselves as we possibly can. So at this point, immediately start plugging in your numbers. When you plug in your numbers, however, be careful about what's what, and especially be careful about negative signs if necessary. So first of all, with this first term right here, I'm going to have 1 times v1 final minus 1 times 3, that's first. So v1 final minus 3. And then our next term is going to be 2 times v2 final minus 2 times 1 for a total of minus 2. So plus 2 v2 final minus 2 is equal to 0. This then simplifies even further. Minus 3 minus 2 is minus 5. So the first of our 2 expressions here, or ultimately the 2 equations, 2 answers, is the following. And then we do the same thing with conservation of kinetic energy. Remember, that's the elastic collision. We're assuming that no energy is lost as heat during the collision itself. But first of all, the basic expression. Change in kinetic energy of 1 plus change in kinetic energy of 2 is equal to 0. So for object number 1, we'll have a final kinetic energy in terms of the symbols, 1/2 m1 v1 final squared minus the initial 1/2 m1 v1 naught squared. So that's our first term. So, okay, then the second object, final kinetic energy, 1/2 m2 v2 final squared minus initial 1/2 m2 v2 naught squared. Once again, just in terms of the symbols. So. And then we start simplifying. Now the 1/2 cancels out even if the masses are not equal. The 1/2 always cancels in the elastic collision. Like so. And then at this point we once again just start plugging in all of our numbers. Just being careful here as we go. So for the first term, I'm going to have 1 times v1 final squared. And then minus 1 times 3 squared, so minus 9. And then plus 2 times v2 final squared. Minus 2 times 1 squared for a total of minus 2. Like so. If you could simplify that a little bit more as well, minus 9 minus 2 is minus 11. So then after we plug in everything and start simplifying, the second of my 2 equations and 2 unknowns then ends up being the following expression. Like so. And then we just have to do the remainder of the algebra. The remainder of the algebra is basically unavoidable. You have to take, first of all, the momentum equation, solve for one of the unknowns, and then plug it into the kinetic energy equation that involves squaring, so we have to FOIL and so on and so forth. All of that is unavoidable. Now when I take this expression here for momentum, which is probably going to be a little bit easier to do, that is solve for V1 final or solve for V2 final? Probably V1 final, because if I solve for V2 final, then I'm going to have fractions. You don't want to deal with fractions. So let's go ahead and solve this for V1 final. I'll do so by taking the 2 terms and moving them to the other side of the expression. So just watch your negative signs as you go. And then take that expression for V1 final. I have to plug it in here, which involves, of course, squaring it. So take this term here for V1 final and multiply it by itself. So. And then I still have this term and this term coming along. Okay, foiling this out. This multiplied by itself is 4 V2 final squared. And then negative 2 V2 final times positive 5 is a total of negative 10 V2 final. But then I have a second one here as well, so minus 20 V2 final. And then 5 times 5 is positive 25, and then I still have my other two terms. And now this starts to simplify for us. So when I start to simplify here, first of all, we've got a 4 plus 2 for 6 V2 final squared. And I still have the minus 20 V2 final. And then lastly, here's 25 minus 11, which is plus 14. Excuse me, myself. Okay, with those coefficients, 6, 20, and 14, what can I actually cancel from each? Just a 2, so let's see. 3 V2 final squared, and then minus 10 V2 final, and then plus 7 is equal to 0. And then we get to this point here. Now, in a problem such as this with small numbers and their own integers, most of the time when you get to this step here, you end up with something that's factorable. Sometimes you don't, particularly if you have decimals and weird numbers. Sometimes you're forced to use quadratic formula, so be it. But in this particular case, we can factor, and even though it is a relatively easy term to factor, to help you ahead of time, you already know ahead of time what one of the answers for V2 final has to be. It has to be 1 meter per second. It has to be the no collision solution. If you don't see the no collision solution in your quadratic, that means that you made an algebraic error somewhere. You missed a negative sign or something like that. In other words, one of the factors here has to be the following for V2 final. If V2 final is equal to 1 meter per second, the same as V2 naught, then this term is equal to 0, and that's the no collision solution. Sometimes you can use the no collision solution, as I'm going to do right here, to then help you figure out what the other factor has to be. So you guys tell me, what does the other factor have to be? 3 V2 final minus 7, that's correct. Like so. So let's just double check. This multiplied by this gives us that. This times this is negative 7 V2 final, and then another negative 3 V2 final for a total of negative 10. And then negative 1 times negative 7 is positive 7, so it works. So if you get to this step and you see the no collision solution, you've done the problem correctly. Okay, other than that, we really don't care about that solution. We're of course interested in this one here. So take this term and set it equal to 0. So that's how you solve for your factors here. And now move the 7 to the other side and just divide by 3, and I get that V2 final is equal to 7/3 meters per second. Notice that's not an integer. It doesn't necessarily have to be an integer. It's perfectly fine if it ends up being some fraction or decimal. Now 7/3 is what, 2 1/3? So that's 2.33 meters per second, like so, as a decimal. Okay, and then lastly, before I demo it, we still need to get the V1 final, but that's easy to do. We just jump back to this opening step of the algebra, and now plug in the V2 final as 7/3. So numerically, V1 final will now be negative 2 times 7/3, and then plus 5. Now the first term here is negative 14/3, and in terms of thirds, what is 5?
15
It's 15/3. So then therefore negative 14 plus 15 is positive 1/3 meters per second, or 0.33 meters per second. So notice that object number 1 continues in its direction of motion. This is a positive number. Continues in its direction of motion, but of course it's considerably slowed down from 3 meters per second to just 1/3 meter per second. So then after all of that, what does this look like? Well, let's see. So here's M1, 1 kilogram. It'll be initially moving in that direction at 3 meters per second. Here's M2, 2 kilograms, initially moving in that direction at 1 meter per second. Collision happens. This guy speeds up to 2 1/3 meters per second. This guy slows down to just 1/3 of a meter per second. So that then looks something like this. So this guy has to overtake this guy. So all of that, just to describe that, that's the one-dimensional elastic collision. Zach?
Can you explain the concept of the no collision solution?
So the no collision solution is just a product of the math. Think of it this way. Because this is all taking place on a horizontal frictionless surface, the momentum of the system is conserved. It's always the same number. This is true regardless of whether or not an actual collision between the objects takes place. So because of this, it shows up as the second answer in our quadratic. The no collision solution is usually what it's referred to as. It's basically just saying that the momentum of the system is conserved regardless of whether or not the objects actually interact with each other. So it's just a product of the math, nothing more than that.
So if they didn't collide, it's just saying that it would continue with.
It's like they pass through each other, if you want to picture it that way.
And they would just have the same.
And they would just all have the same velocity. That's right. So the momentum is conserved regardless as to whether or not the collision takes place. That's the easiest way to picture it. Yeah.
Compared the engine file because with the.
With the V2 not.
Because it's the same, it's like.
Yeah, it's saying the collision doesn't happen. So as a product of the math, you have to see that come out of the quadratic. So if you don't see it, that means you made an error somewhere. You missed a negative sign or added something incorrectly, something like that. And then it's 20 out of 25 instead of 25 out of 25. Okay, that's the one-dimensional elastic collision. But then, of course, the fun really begins now with the two-dimensional elastic collision. Let me erase all this junk. And now we get to the two-dimensional elastic collision. As we'll see, however, we're actually only going to look at one situation. Now, with regards to the two-dimensional elastic collision, we never picture the problem from a point of view or a reference frame where the collision looks like this. Objects come in, glance off each other in some manner, and then come apart. They scatter off of each other, as we say. The reason why we never pictured a problem from a reference frame that looks like this is just because there's just too many variables. For example, each individual object comes in at different angles, they then glance off each other, and then you have more angles to deal with. Mathematically, that's a huge mess. So we never picture such a collision from that point of view. We always picture a two-dimensional elastic collision from a very specific reference frame. A reference frame where one of the objects, target, is initially at rest, and then the other object, the incident particle, is initially moving along the positive x-axis only. And then the objects glance off each other, and they then scatter. Think of it as a pool analogy once again. You have your target, the target ball, and you have the cue ball, the incident particle. We always think of the cue ball as coming in along the x-axis like so, the target ball being initially at rest, and then the objects just glance off each other like so, resulting in a two-dimensional elastic collision. So we always picture the problem from that standpoint. We're only going to look at one type of situation, and that's, once again, using the pool analogy, objects of equal mass. The cue ball and the target ball have the same mass. That's the only situation that we have to look at. Henry, you're about to ask something.
Yeah, but what if the object that that the target ball is representing is moving?
Okay, then you have a picture that kind of looks like this, for
Right.
example. That's just mathematically a huge
Okay,
mess.
so we're not going to do that.
So for our introductory purposes, we're just going to
Right.
simplify the diagram considerably. Think of the target initially at rest. The incident particle, the cue ball, comes in along the x-axis. They then glance off each other and do something like this. Now, those of you that are familiar with playing pool, as you'll see in a glancing collision, essentially only one thing can happen. We'll approach this using two problems. First of all, I'll do a numerical problem that will illustrate what happens, and then after that, we'll take a look at a nice, elegant proof of the situation. I'll also eventually demo it for you here using this Airtable. Anything, you have any problems with your second period teacher today?
Fourth period, no.
Fourth period.
Yeah. And then he makes those taking my picture for your romance.
Romance?
Which one?
Okay, even though we simplify the picture considerably, and of course I'll draw this out for us in just a moment, the two-dimensional elastic collision problem is still algebraically a big mess. So this is one of the messier problems algebraically, frankly, that you see in this entire class the entire year. Okay, notice that the masses of the objects are not givens. That's okay. It will eventually all cancel from the expression anyway. But as you read through the problem, ultimately there are three unknowns, two final speeds and an unknown angle. So because there are three unknowns, this means that algebraically we need three equations. That's why this becomes a mess. Okay, a typical scattering diagram, as they're sometimes called, is drawn in the following way. Once again, we'll use the pool analogy here. So first of all, we have our cue ball of mass m, initially moving in this direction with a v1 naught equal to 1 meter per second. Okay, and then we've got the target ball like so, also mass m. This one's initially at rest, v2 naught is equal to 0. And then the balls glance off of each other. We're given that the first ball, the cue ball, moves off like so, with an unknown final speed, v1 final, but we are given its scattering angle, as it's called. This angle here, call it theta with respect to the positive x-axis, is given to us at 16 degrees. Now, in a two-dimensional elastic collision problem such as this, one of the angles is always going to be a given. And the reason for that is as follows. Think of the pool balls as spheres, or equivalently, just think of these two rolls of tape. It's literally the geometry of these rolls of tape, how they actually undergo the collision itself, that determines what one of the angles is going to be. So for example, if I take the two pieces of tape and offset them from each other like so, when they glance off each other in this manner and exert forces on each other, then that's going to determine what one of the angles, in this case theta, is going to be. However, if I take the two pieces of tape and instead of having them really offset from each other, only maybe slightly offset from each other like so, and then they interact with each other and glance off each other doing something like this. So it's the geometry of the objects themselves that determines, in terms of what happens with the forces between them, what one of the angles is going to be. We're going to ignore that detail. We're just going to think of the objects as points. So because of that, then, at the introductory level, one of the angles is always going to be a given for that reason. So this angle here that's given is basically determined by the geometry of the objects. Okay, we'll ignore that detail. We're just going to treat the objects as points. We will ignore detail. We'll treat the objects as points. So suffice it to say, one of the angles is always going to be a given in a problem such as this. Okay, but then we have the target ball. That scatters as well. The target ball does presumably something like this. Well, right here is once again mass m. We have an unknown final speed associated with that, v2 final. And then right here is an unknown scattering angle, typically referred to as phi. So immediately, even though one of the angles is a given, there are still three unknowns. v1 final, v2 final, and the angle phi. This means three equations. So what are the three equations? Well, the first two equations are just conservation of momentum. It's a two-dimensional problem, so we look at the x components and then the y components. And then after that, the third equation is conservation of kinetic energy, ultimately resulting in three equations and three unknowns. And algebraically, as you'll see, this is a bit of a mess for that reason. Okay, now the first of the expressions is conservation of momentum in the x direction. So like we saw in previous two-dimensional problems, we have the following notation associated with our conservation expression. And now we just fill in all of the terms here where basically everything is going to be in terms of a cosine. So first of all, for object number one, its final momentum in the x direction is its mass m multiplied by the x component of v1 final, which is v1 final cosine theta. Like so. Then minus the initial momentum of number 1 in the x direction, which is just m times v1 naught. And then we have change in momentum of number 2 in the x direction. Its final momentum in the x direction will be mass m multiplied by the x component of v2 final, which is v2 final cosine phi. Minus then its initial momentum, which is equal to 0, because the target, remember, always begins at rest. And then if we clean up this equation a little bit, the mass cancels out from the expression, and the expression then therefore becomes the following. So after I canceled the masses and cleaned it up a bit, the first of our 3 equations as we get is this expression here. Okay, next we set up our conservation in the y direction, and basically all the cosines here just turn into sines. So first of all, the notation itself, change the momentum of number 1 in the y direction, plus number 2 equals 0, start filling in our terms. So, yes, go ahead, sorry. V1 cosine theta, whoops, V2 final cosine phi, thank you. Yeah, check me as I go, especially after I've been doing this now a couple of times today. Okay, so now in the y direction, doing this nice and careful, final momentum of number 1 in the y direction is m v1 final sine theta. Okay, minus then the initial momentum of number 1 in the y direction, which is 0. Remember, he begins in the x direction only. Then object number 2, final momentum y direction, m v2 final sine phi. 2 final sine phi. Minus then the initial, which is 0, because that object begins at rest, like so. Okay, once again, the mass m cancels out. So if we cancel out the masses m and then just kind of toss away the parentheses and whatnot, the second of our 2 equations, making sure that I write this correctly, is as follows. So those are the first 2 expressions, and then the third equation is just conservation of kinetic energy, all the 1/2 mv squared. Now remember, there's no cosines or sines in kinetic energy. It's just final minus initial of 1/2 mv squared for each of the individual objects, just like the one-dimensional problems from earlier. So our third equation then comes from the following. Change in kinetic energy of 1 plus change in kinetic energy of 2 is equal to 0. So first of all, for object number 1. For object number 1, its final kinetic energy is 1/2 m v1 final squared minus then the initial 1/2 m v1 naught squared, like so. And then now object number 2, final kinetic energy, 1/2 m v2 final squared minus the initial, which is equal to 0, because remember the target begins at rest. Okay, once again, the 1/2 cancels, it always does in the elastic collision, and the mass m here cancels out as well. So then therefore, after you cancel the 1/2 m's and clean up the expression a little bit, it then ends up being the following, like so. So this is the setup. This is basically now getting our 3 equations. And at this point, it's now 3 equations, 3 unknowns. So how do we go about doing this? Well, notice immediately in the first 2 expressions that one of the unknowns is an angle. There's a cosine of phi here, and there's a sine of phi here. How do we get rid of an angle from a set of expressions? Well, we actually did this once. We did this in a Galilean relativity problem back in chapter 3. There was a very difficult problem in chapter 3 involving Galilean relativity with a plane, where one of the unknowns was an angle. And in our equations, we had a cosine of that angle, and we had a sine of that angle. Does anybody remember algebraically taking advantage of a very specific trigonometric identity? Does anybody remember how we got rid of that angle? No, not small angle approximation. What trig identity did we take advantage of? You said 1. Which trig identity is equal to 1? Cosine squared plus sine squared. You square the equations and add them together. So you're seeing that algebraic process here for the second time in the context of this problem. So you see that algebraic process in this class twice. You saw it once in chapter 3, you see it here again as well. Basically what we have to do, and this is kind of like the rough part of the problem, is I have to take this top expression first, and on the right-hand board, I'm going to write it in terms of V2 final cosine phi, basically my unknown angle. And then with the second expression, I'm going to write that in terms of V2 final sine phi. I'll then square the equations and add them together. When I do, I'll get eventually a cosine squared phi plus a sine squared phi, which is 1, and then I eliminate the angle from my set of expressions. So that's the process. It does take a few minutes to do. So now, taking the top expression, I'm going to write it for V2 final cosine phi. So I'll take the other two terms and move them to the other side. That will then give me this without making any mistakes at all, Dave. Okay, then I'll take this bottom expression here and I'll write it in terms of V2 final sine phi by moving this guy to the other side. Yes, for big yawns too. And yes, I know trigonometry is yawning. So, okay, now before I square and add, I'm going to clean up my boards a bit. Get rid of the junk I don't need. I don't need this stuff anymore. So what I'm going to do this junk here. Let's get rid of that. And here comes the mess. First I have to square this. Now squaring the left-hand side is easy. Squaring the left-hand side of that top expression just gives me this. So, but now when I square the right-hand side, I have to FOIL that thing. I have to take this and multiply it by itself. Yuck. Like so. So multiplying that by itself on the right-hand side, what do I get? Let's slow down. Okay, first this times this. And then I've got this times this, but then a second this times this. Like so. And then this multiplied by itself, which is this. So. Oh yeah, it's a mess. I'm sorry? No, it's not optional. Because the reason why is that this problem will give you the second strategy that you need in making sure that you understand how to win in playing the pool. Because as you'll see from the results of this problem and the proof as a follow-up, as long as you don't strike the cue ball into the target ball head-on, only one thing can happen. That's what we're going to ultimately see towards the end of this problem. Okay, just before I get there, however, now we'll take this guy here and square that. That's actually easy to do. And then what I have to do is add the equations together. Now when I add the equations together on the left-hand side, I'm going to get a cosine squared phi plus sine squared phi, which is 1. It will disappear from the expressions. And then also here on the right-hand side, when I add a cosine squared plus sine squared over here, I'm also going to equal 1. I'm going to see the same trig identity twice. Shruti, you got to stay with me. I know it's difficult. But now here's then what I get.
Wait, isn't it negative?
Oh, the negative sign here squared.
Oh, well.
That's squared out, okay? Okay, so now adding the left-hand side first. When I add the left-hand side, I can factor out from each term the common V2 final square, giving me this on the left-hand side. And now on the right-hand side, when I add together here, I first of all have these two terms, like so. But then I also have this and this added together, where the V1 final squared is common to both. So I can factor it out and I see the exact same trig identity. It's at this point forwards that things start to simplify. What I just did getting to this point here is kind of the hard part. After this, it's fairly straightforward. Okay, now in parentheses on either side of the expression is 1. So this is just V2 final squared times 1 over here, and then over here in this term is V1 final squared times 1. So at this point, things start to simplify. So then therefore, the next step of this green process here is this. V2 final squared now on the left equals then this stuff here on the right. Like so. I'm going to clean up the board here in just a moment. So that last green step that I wrote down, that last green step is basically these two equations here that I started this process with, algebraically combined together. Notice that the angle phi is gone. So now that the angle phi is gone, what the heck is left? Well, at this point, what I have is 1, 2, this purple equation, the energy equation that I haven't even touched yet. 2 equations and 2 unknowns. The 2 unknowns are V1 final and V2 final. So at this point, I can now solve for them. Once I have those 2 speeds, V1 final and V2 final, the last part of the process is just to jump back to here and figure out what the angle is, and then arrive at the punchline. So you can make sure that you can win and play pool in the future. Remember, at this point forward, I get a cut of your winnings. Before we get there, however. So what do I do next? Well, what I do is I take this expression that I've arrived at here for V2 final squared, and I now just plug it into there. This will then allow me to get the V1 final squared. Now she said, oh my God, don't worry, it's already squared. It's already squared. So you don't have to square it again or do anything crazy like that. All you gotta do is plug in to the energy equation. I told you this was algebraically the worst problem that you'll see the entire year. Yeah, this is the algebraically worst problem that you'll see the entire year. After this, it's just smooth sailing, right? After this is all easy. All right, so I have to plug that thing into the energy equation. So, doing so, I have first of all these 2 terms here. And as I start doing this, things will start to simplify. Okay, now take this green thing here, just plug it into there. Like so.
You know what calls a shortcut?
No, there's no shortcuts. Okay, now, notice that a couple of things here cancel out and add together. We have a negative V1 naught squared and a positive V1 naught squared. Those guys are gone like so, so that's good. And then I've got a V1 final squared plus itself over here for 2 of them. So if I now start adding those together, I watched my March 6 Days a couple of weeks ago. Okay, now what happens to the tubes?
That's wrong.
Wow. What else actually cancels from each term? V1 final. Now, here's what's left. V1 final is equal to V1 naught cosine theta to the other side. And I now have the first of my unknowns. So let's start to see now what the numbers give us. So I'm going to have 1 times the cosine of 30. Cosine of 30 is root 3 over 2, right? Or the heck that is, this is a decimal. Cosine of 30 is 0.87. So the first object's final speed is 0.87 meters per second. Okay, now that I have that speed, what do I do next? Well, what I now do is just jump back to, say, this green expression here, plug in everything, and now find the V2 final. So let me do that. So what I'm going to do is 1 squared minus 2 times 1 times 0.87 times cosine of 30 plus 0.87 squared. Take the square root. So all that. 1 root 1 minus 2 times 1 times 0.87 times cosine of 30 plus 0.87 squared. Take the square root of that stuff. Everybody sing it as you go. And you get V2 final equals 0.5 meters per second. So once again, that came from taking everything that I now have, plugging it into the green expression here, taking the square root of it, and get that. And then lastly, we get to the angle phi. Just jump back here to find the angle. Before I do, can anybody tell me what is the answer? Those of you that play pool, that is if theta is 30 degrees on the board, Griffin, what are you supposed to find is it's 60 degrees. He's exactly right. Here's how we show that. So what I'm going to do is take this expression and solve it for cosine phi. And I'm also going to take the bottom expression and solve it for sine phi. The reason why I'm going to solve for both is because I want to show, in fact, that yes, the angle phi is in the fourth quadrant. I want to be quadrant specific here. So how do I do this? Well, in the top expression, what I'm going to do is 1 minus 0.87 times cosine of 30 divided by 0.5. So 1 minus 0.87 times cosine of 30 all over 0.5. And that comes out to be 0.5. And then in this expression, to get sine phi, I'm going to do negative 0.87 sine of 30 over a half. So negative 0.87 times the sine of 30, sine of 30 over a half. And that comes out to be negative 0.87. So if you get a positive cosine and a negative sine, into which quadrant then is the angle phi? Fourth quadrant. And then yes, Griffin is in fact correct here, because the cosine of what angle is equal to right here? Cosine of what angle is equal to 60 degrees? It's a 60-degree angle. Notice that the sum of the scattering angles, 30 plus 60, is 90 degrees. It always will be in the two-dimensional elastic collision problem between objects of equal mass where the target is initially at rest. The sum of the scattering angles is always going to be 90 degrees. So now that you know that, this is then the second strategy that you need into making sure that you can win in pocket billiards. Because if you don't spin the cue ball, only one of two things can happen. Number one, it's a head-on collision, and the cue ball ends up at rest, and the target ball ends up with the cue ball's original speed. Or if you do glance the balls off of each other, the sum of the scattering angles is always going to be 90 degrees. Those are the only two things that can happen. So if you watch really good pool players, they know this, and they're taking advantage of it over and over and over. Because all that they're doing from shot to shot is setting themselves up for the next shot such that one of the two things can happen. Every now and then they may have to resort to tricks like spinning the cue ball to set themselves up for the next shot. But if you watch really good pool players, shot to shot they're always making it as easy on themselves as possible such that only one of the two different things happen. Griffin?
Oh, no, I didn't.
Yeah. So that's, in other words, the only thing that can happen if you glance a cue ball off of the target ball, as long as you don't spin the cue ball, they come off at right angles. Now this was not a specific proof of this, this was just a numerical example. After we take a short break, then I'll run through the specific proof, which is actually very elegant and very short. So let's take a short break. Yeah.
So if you, so I just shot the drill ball.
So if you glance the cue ball off the target ball, as long as you don't spin the cue ball itself, it just rolls along the felt. When it glances off, it'll always glance off at a right angle. No, if you hit the cue ball head on to the target ball, one-dimensional collision, then yes, the cue ball will stop. But if you glance the cue ball off the target ball, they will come off at a right angle every time.
I do that to myself.
You're not to wear costumes?
That'd be good film and maybe just
So you don't have to hold it. Just pee in the ocean after class.
There's a lot of good
As soon as it comes back, you are you in danger of losing it right now? Yeah, that's one of the longer problems you see. It's kind of a mess. This is why people write code.
You wasn't. Your face is hilarious.
We shot it through.
like,
You should have you guys can have an algebraic process. They should have gotten you a picture of you guys like sitting here working on your physics.
I feel fine. Okay.
That one happened.
It's an algebraic romance.
She got sick 3 days ago. So.
Is that going into your book?
Yeah, for the next like 10 weeks, that's why.
Did you have to go down to Mr. Sal's room?
Yeah. Never had one before. It's like the worst in the world. I've never had it.
Yes. How about that? Just every page. Just every page.
The whole year.
That's the entire yearbook. It's just Nathan in a mirror. It's it.
It's sore throat, swollen.
You don't mind everything else. Screw it.
So that's what was on your wall?
Huh?
The thing on Vice.
Oh, yeah.
I read it, he was like, the subtlest things pissed me off, like why did they have me drink water out of an open glass when they know that I'm like.
I had actually heard about that
How
experiment a
long does
couple
it
of
take
months
to get
ago.
one?
They're kind of like studying, you know, once again, what happens, you know, like in long duration space flight if you don't use your musculature.
He said he was tilted
Bad
at
things
like
happen.
60, negative 60 degrees in air.
Frankly, I mean, okay, they gave him 18 grand to do it, but I'll bet you it was cool.
Yeah.
This is the
But
usually
yeah, really
6
was
weeks
cool.
after the virus.
Better pay 18.
He said, the first time he brought up after.
Yeah, he couldn't stand for 15 games.
Yeah.
I'm not surprised.
She probably was only else because I didn't know.
I heard of this one experiment, I'll mention this a little bit later when we start talking about light. And I remember hearing about this one experiment that some graduate school students did on vision, where they fitted onto the people's heads some glasses that actually flipped their vision. So you would see it as upside down by using these glasses. And they then had to live like this for a month. And of course, when they first of all had the glasses on, they were all stumbling around and so on and so forth. They couldn't stand up straight, etc. But after a couple of days, their minds, their brains started to adjust to the different sensory input. And by the time of the end of the process, it was like they were perfectly fine. They could ride bikes and drive cars and do everything else that you normally would do. And then at the end of the process, they took the glasses off of people, and then they were all stumbling around again until their brains essentially readjusted. So your brains can adapt to changing conditions. But something like that with that person lying prone basically for, what was it, 70 days? Yeah, that would be grueling. That would be so bad. I wouldn't be able to take it. I wouldn't be able to take it. I wouldn't be able to do it.
Well, yeah, but he says
There's a lot of
Yeah, we gotta get rid of that, yeah.
Okay, let's go ahead and take a look at the proof. Okay, Sean, don't worry, when the bathroom pass comes back, you can just grab it. All right, now, to finish today's lecture, yes, we'll see the Mechanical Universe episode of Momentum afterwards. Let's take a look at the following proof. Now, the numerical example that I just did was just a numerical example. I just showed that in that situation, if theta was 30, the angle phi was 60 degrees. Strictly speaking, that's not a proof that the sum of the scattering angles is always going to be 90 degrees. We'll take a look at that proof here. The proof is actually very simple and elegant. It's actually only a couple of steps, and I'll take you through it here, however, slowly. So prove that the sum of the scattering angles is 90 degrees for two objects of equal mass undergoing the two-dimensional elastic collision, or one of the objects the target is initially at rest. Yeah?
So can we take advantage of this property and like, okay, like plug it in and.
Yeah, because if you know ahead of time in that last example that phi was 60 degrees, then solving for V1 final and V2 final is actually just two equations, two unknowns, so it's easy. Okay, how do we end up showing this proof? Well, it's done in a very elegant manner. One of the things that we actually don't do is we don't write everything in terms of velocity vectors, like the last example. Instead, what we do is we just write everything in terms of their momentum vectors. And it's actually not necessary to break everything up in x and y components. We can keep everything in vector form for this proof. This then leads us to the following scattering diagram. So we're going to have our first object here with initial momentum now, just p1 naught, like so. And then we have our target here, still of the same mass. This object is initially at rest, so its initial momentum p2 naught is 0. And then the objects scatter off each other, like in the last example. So object number 1 goes off like so with a p1 final as its final momentum vector. And then still with respect to the positive x-axis, we have our first scattering angle here, theta. Okay, then we have the second object, the target ball and pool. Once again, to use that analogy, scatters off like so. We have here its final momentum vector, p2 final like so, where once again, right here is our scattering angle phi. So in terms of the diagram, what the question is asking us to do is it's asking us to prove that theta plus phi is equal to 90 degrees. So that's a statement of the problem in terms of my diagram. Okay, now as I said, we just keep everything here in vector form. We actually don't have to break everything up into components. So we have our first equation, which is conservation of momentum, once again. No cosines or sines are necessary here, just keeping everything in vector form is perfectly fine. So first of all, for object number 1, the change in its momentum is just the final, p1 final, minus the initial, p1 naught. And the first term in vector form just looks like this. And then we have our second object, the target, final minus initial. Final momentum is p2 final minus the initial, which is 0 because the target begins at rest. Like so. And now if I just clean up this equation by doing the following, moving the p1 naught to the other side, all that I end up with is a vector addition equation. I just end up with the following. p1 final plus p2 final is equal to p1 naught. Now all this expression says, by the way, is that all the initial momentum before the collision equals all the momentum after the collision. But it is a vector addition equation. When you add two vectors together to get a third, if you go all the way back to the basics of vector algebra that we did back in chapter 3, what sort of geometrical figure is formed? Just a triangle. It's just a vector triangle. So using the tail-to-tip method of vector addition, here's what our vector triangle looks like. We first of all have P1 final, which is this guy here. Watch this. So, and then I'm going to add to that P2 final this guy right here using the tail-to-tip method of vector addition. That's this right here. And then they equal P1 naught, which is this guy here. That's this vector like so. Okay, now on this vector diagram, where are my angles theta and phi? Well, pretty obviously, the angle theta, first of all, is right here. Remember that P1 naught is entirely along the x-axis by definition to begin with, and then P1 final makes an angle with respect to that axis at the angle 30, or the angle theta, excuse me, on the diagram above. And then on the diagram above, we have the angle phi. Where is that here? Well, let's point the marker here along the x-axis like so, and so then therefore the scattering angle of P2 final is right here. That's the angle phi. However, the marker here is parallel to P1 naught, because P1 naught is also in the x direction. So therefore, this angle phi right here is the same thing, then therefore, as this angle here. Okay, now, if theta plus phi is equal to 90 degrees, what type of triangle is this? It's a right triangle. So how do we prove that it's a right triangle? This is where kinetic energy comes in. However, before I show this explicitly for the proof, we have to come up with, briefly, another way of describing kinetic energy. Now, as we've seen it, of course, over and over in examples since chapter 7, kinetic energy is 1/2 mv squared. But this proof is not done in terms of velocity vectors v, it's done in terms of momentum p instead. So then therefore, in order to apply kinetic energy to our problem here, I have to come up with an alternate means of writing kinetic energy. We do so in terms of momentum. Here's how we do that. Now momentum, p, is equal to just mass times velocity. All I'm going to do here is solve for the velocity, which is the momentum divided by the mass, and then just plug it into here. This will be an alternate way of writing kinetic energy, but specifically in terms of momentum is necessary for this proof. So if I plug momentum over mass into the expression here and square it, then kinetic energy K is 1/2 m times p squared over m squared, like so. If you cancel out an m here and here, you end up with p squared over 2m. So p squared over 2m is still kinetic energy, it's just specifically in terms of momentum. It's necessary here. And now we set up an elastic collision. Elastic collision, change in kinetic energy of 1 plus change in kinetic energy of 2 is equal to 0. And now we just start filling in our terms. And when we do, we write the kinetic energies as p squared over 2m. So first of all, for object number 1, its final kinetic energy is going to be p1 final squared over 2m minus its initial p1 naught squared over 2m. The first term is like this. Okay, then we have the second object, remember still of the same mass. Its final kinetic energy is p2 final squared over 2m minus the initial kinetic energy of 0 because it begins at rest. So this second term looks like this. Because the masses are equal to each other, notice that the denominators of the expression all just cancel each other out. And now only one more step is necessary here for our proof. I'm going to move this p1 naught squared to the other side, and I get this. So, and now you guys tell me, what is this about that triangle? It's Pythagorean theorem. So because it's Pythagorean theorem, that means that, yeah, this is a right triangle. If that's a right triangle, then therefore, the sum of the scattering angles, theta plus phi, is equal to 90 degrees. Very nice, elegant proof. It's basically two steps. The first step is conservation of momentum to get the vector triangle. The second step is conservation of kinetic energy to show that it's a right triangle. It's basically a two-step process. So when you have a pool ball, glance off of another one, as long as the balls are of equal mass and the target is initially at rest, the sum of the scattering angles is always going to be 90 degrees. Okay, let me demonstrate this for you using this air table. Okay, this air table is basically the same thing as an air hockey table. By the way, if you want to play me for money in air hockey, you can see me after class as well. We can do that for darts, bowling, Call of Duty, whatever. I'll clean out your wallets for you.
Even Call of Duty.
Yeah, I'll clean out your wallets for you.
Xbox or PlayStation?
Xbox.
Yeah.
Okay, so what I have here is a demo. Is that I've got these two pucks here of equal mass, and I'll turn this thing on, and it's basically a horizontal frictionless surface. It's really loud, however, it's kind of a pain in the butt. But what I'll do is I'll basically glance these pucks off of each other, well, I'll try to keep one of the pucks, the target, initially at rest. In other words, right before the collision happens, I'll just let go of it. Now, I can't tilt this towards you or anything like that, so you guys in the back are going to have to stand up and basically what you want to watch for is what happens after the pucks glance off of each other. I'll do this a couple of times so you can see, but they're always going to glance off of each other such that they form a right angle. So just watch it happen here a few times. As I said, this ain't really loud. Right angle. Right angle. Right angle. Right angle, and so on. They always glance off each other at a right angle. If you want to try this for yourselves, by the way, at the end of the period, you're
Wait, you guys sit, don't sit down. No, don't sit down. No, these are perfect lines.
right, let me do it.
What's over here? Fine, I was gonna see if there's something.
Okay, stand up. I'm saying. What are we doing?
Turn around. Oh, it doesn't matter. Go away.
What are you
I don't know,
like
sorry.
AT&T raising the bar?
It looks part of the thing.
All right, have a seat. One, two, three, four, five. 1, 2, 3, 4. Hang on a second. 4 short. Yes. 1, 2. Hang on a second. I'm 4
Oh,
short.
yeah.
I never learned how to do the movie.
What?
In 8th grade, they told me for donuts, I just used bullet points. My teacher just let me, I never really learned how to use bullet points. Yeah, I know, but like, I noticed the summary at the end of the notes. So like Miss Bank.
Oh, yeah. I'm printing water.
Okay, sorry, a little bit short here. Yeah, so one more down in that direction. Hot off the presses.
Warm? Give me one.
All right, so yeah, we have the Mechanical Universe episode of Momentum. This episode I like a lot. There's a lot of good stuff for us to examine here in the context of the episode. As always, please take Cornell-style notes, and I will collect them from you at the beginning of the period next time.
We'll go ahead and get this thing started. How long?
9.
It'll take us towards the end of the period, don't worry.
Funding for this program was provided by the Annenberg CPD project.
The momentum of an object is equal to its mass times its velocity. When no external forces act on a system, the total momentum is constant. This principle is called the conservation of momentum.
One of the effects of the trial of Galileo was to expel the scientific revolution from Italy. It eventually came to rest, of course, in the person of Isaac Newton in England. But on its way north, it stopped off in France for a while to visit René Descartes. I haven't said much about him up to now because I didn't want to put Descartes before the course. Descartes understood straight lines. That might not seem like much to you, but it led to the invention of Cartesian coordinates, which are named after Descartes, although he didn't invent them, and to the principle of inertia, which Galileo hadn't quite gotten straightened out. Descartes was a great scientific optimist. He thought that we would come to understand everything we needed to know in a few years if we would just follow a few rational principles, which of course he was kind enough to lay out for us. One thing he deserves credit for is the idea of the mechanical universe. That is, a universe that would inexorably work out its destiny following precise mechanical laws. It was rather like a clock, or one of those exquisite mechanical toys the craftsmen of his era used to make. But the analogy broke down in one important respect. A clock has to be wound up from time to time. And Descartes did not want that kind of intervention from the creator of his universe. And so he needed some principle that would keep the universe running forever. And the one he hit upon was the idea that the total quantity of motion in the universe was fixed. That is, if one thing slowed down and came to rest, another body would have to speed up and start moving. That idea eventually became the law of conservation of momentum. And that's our subject for today.
Now, of course, you guys have all seen that device before. I have an example of it here on my desk. The device itself, by the way, is called Newton's cradle. The way that Newton's cradle works is actually very simple. It's essentially just a combination of two things, conservation of energy and conservation of momentum. So, for example, if I draw up this first pendulum like so, I give it some potential energy, let go of it, it turns into kinetic energy as it swings downwards. And then basically what you have is a series of one-dimensional elastic collisions here between objects of equal mass, where the target is always initially at rest. So then ultimately what happens is that this pendulum over here emerges with the exact same momentum like so in this direction that this pendulum on my right-hand side originally had prior to the first collision. And then of course it swings up to the exact same height. So you're basically just seeing a combination here of conservation of momentum and conservation of energy when we just do something like this. But if you play around with this a little bit, you could actually come up with some nice patterns, some of which are aesthetically pleasing. For example, you can have two like so, and then out the other side. Okay, 3 and 2 is kind of interesting. I kind of like this one. That's kind of nice. Okay, 4 and 1 is kind of neat too. Like so, and then watch this, here's my favorite, 5 and 0. Like so. But regardless of what you're seeing here, of how complicated it may look initially, it's really just a combination of conservation of energy and conservation of momentum. You can also do stuff like this on either side. So watch what happens when you do 3 and 2 on either side. Like so. We'll say 4 and 1 on either side. Like so. But once again, you can come up with these neat little patterns here, but it's really just a combination of the two things. Conservation of momentum and conservation of energy.
These men live by certain laws. Sometimes beyond the gambling statutes of the city and county of Los Angeles, but well within certain laws of classical mechanics. They make their living off the art and science of pocket billiards.
Not a good way to make a living.
Not every man enters Chalky's Billiard Academy to illustrate the conservation laws. Not every man here fully appreciates the fact that, win or lose, classical mechanics governs the game of pool. Most walk down Chalky's narrow stairs to shoot a stick, or to profit from the experience by some other means. But odds are, when certain laws of physics are applied just right,
Spin the cue ball.
every man here fully appreciates the effects. Of course, while a billiard ball may obey those laws perfectly, the principles behind them didn't originate in Chalky's Billiard Academy. Some of those principles, like the game of pocket billiards itself, originated in France. As a youth in the Catholic France of the early 17th century, René Descartes came to love the trappings of mathematics as the workings of God. He loved the power of a finely reasoned argument, and the glorious feeling when a concept could be understood in the absolute.
Now pay close attention here.
But Descartes lived at a time when, not unlike today, the glories of God and the power of reason didn't always exist in perfect harmony. In 1600, when 4-year-old Descartes was just beginning to come to terms with the Europe around him, a scholarly monk named Giordano Bruno was burned at the stake for, among other things, his beliefs in the Copernican system of the universe.
Now you remember this man, you remember Giordano Bruno, and you remember how and why he died. I certainly have. He deserves a spot on my arm, which is right here.
Eventually, Descartes, like Galileo, was a Copernican, but unlike Galileo, who was tried in Rome for expressing himself to one and all, Descartes withheld publication of similar views when they flew in the face of the Mother Church. To some scholars, Descartes is remembered as a cowardly hypocrite. Others remember him as a sincere, devout, and devoted Roman Catholic. As for Descartes himself, he probably just remembered what happened to Giordano Bruno. In any case, it was Descartes who first enunciated this principle. The total quantity of motion in the universe is constant. If a body is not interfered with, it will move at constant speed in a straight line. That's the law of inertia, Galileo's idea, perfected by Descartes. But when a body does meet others, it isn't merely brought to rest. It transfers its motion to the other bodies. The total quantity of motion is conserved. Though Descartes was the first, the essence of his quantity of motion was in fact expressed better by Isaac Newton. Of course, as competitive as he was, it's doubtful whether Isaac Newton ever challenged a colleague to a game of pool. His challenges were to the intellect alone, and none of his expressions was more powerful and moving than his idea of momentum. In his classic work, The Principia, he wrote, "The change in motion is proportional to the force impressed, and it is made in the direction of the straight line in which the force is impressed." Newton used the word motion to mean momentum, or in modern terms, the velocity of a body multiplied by its mass. In his own field, Newton chose to express most of his powerful ideas with classical geometry, using geometric figures and ratios between quantities. But he was skilled enough to know that his laws could be expressed as differential equations. According to Newton's second law, the impressed force is equal to the rate of change of momentum. Newton's second law.
Now wait a second, that's not quite how we saw it back in the first semester when I first taught you the laws of motion. Back in the first semester, we of course saw Newton's second law as just F equals ma. However, it turns out that this is actually only for cases when the mass of the object or the mass of the system is a constant. What happens if the mass of the object changes? Now, what would be a situation involving a changing mass? Well, say a rocket ship. A rocket ship accelerates by means of thrust by expelling gases out of the rear of the rocket. So the mass of the rocket is decreasing with time as time goes on. So how would you then apply F equals ma to a situation such as that? Well, it turns out that this expression here, how we saw Newton's second law originally, is actually a specific version of a more general expression. And that general expression, what they just described in the film, is the following. Now remember that acceleration, of course, is the derivative of velocity with respect to time. However, this quantity here is actually the same thing as this quantity here, like so, when the mass is constant. When the mass is constant, you can pull it out of the differential like so, and you basically have F equals ma. But this quantity here is momentum. So a more general way of describing Newton's second law is that the sum of the forces results in a change in the momentum of the object with respect to time, or a change in the momentum of the system. This is the most general way of writing Newton's second law, and it can be applied to any situation involving, for example, situations where the mass of the system is changing in some manner. So this is a much more general expression. This is the true statement of Newton's second law, whereas this is kind of like the simplified version, if you will. However, we teach you this version first because it's the easiest to deal with, and now you get introduced to this more general way of describing it here in chapter 9.
Moving, powerful, and everywhere in the universe, an idea with an enormous impact. Interactions around this table are complex subjects of social science. Interactions on this table, however, are purely physical in nature and comparatively easy to explain. Again, according to Newton, a single particle of some definite mass has a momentum equal to m times v, and the change of momentum can be expressed by a differential equation. Force is the rate of change of momentum. Of course, if there are no forces operating, the derivative is equal to 0. Therefore, the vector p is constant, which means the motion of the thing itself is constant.
Newton's first law, the law of inertia.
A body with no forces acting on it will continue moving at the same speed in a straight line. This is the law of inertia, Newton's first law. But when billiard balls collide,
Watch this.
each one applies a momentary force to the other, causing its momentum to change. Here, Newton's third law gets into the action.
Those are internal forces.
The forces the balls apply to each other are equal and opposite. The change in momentum of one ball is, therefore, equal and opposite to the change in the momentum
There's
of
our
the other.
conservation equation.
The
Written out in
total
differential
momentum
form.
of the two balls taken together does not change at all. It's constant. In
No,
fact, this new law
Watch
applies
this.
not only to two balls when they strike,
Some is the
but to
same.
any number.
And not only to the billiard balls themselves, but to the very atoms of which they are made. And even in the inner parts of the atoms, the electrons and neutrons and protons, right down to the ultimate constituents of matter itself, momentum is always conserved. But there's an easier way to win the game than to keep track of the countless electrons and protons and neutrons in each billiard ball. Even though each ball is composed of atoms and smaller parts, applying equal and opposite forces to each other, each ball behaves as if it were a single body with all of its mass concentrated at a single point. That point's called the center of mass, and in this situation, it's one of the more explosive ideas in physics. The center of mass is the point to focus on when calculating the velocity and acceleration of a compound body. When no net outside force acts on a compound system, no matter what happens to its individual parts, the center of mass continues to move at constant speed in a straight line. In deriving his second law, Newton might have imagined a collection of compound bodies, not necessarily touching each other.
Watch this.
Two bodies of nearly equal mass. Or perhaps better yet, two bodies like the Earth and the Moon. He knew hidden forces were at work up there. Gravity, for example. Conversely, he could imagine that external forces were not at work on such a system. Then the system wouldn't be accelerated. Its center of mass moves with a constant velocity. If the planet pulls on its moon, then the moon pulls on the planet with an equal but opposite directed force. The vector sum of the two forces and the derivative of the momentum of the bodies are equal to 0. If the derivative of something is equal to 0, that something is constant, and that constant, the sum of the momenta of all the bodies, is a conserved quantity.
Okay, now, back in chapter 6, there are some details here, of course, that we ignored when talking about gravity. For example, when we talked about situations of involving one object or another, with one exception. We always thought of one of the objects as being stationary at the center of a circle, the Earth, for example, and then just to keep things easy, the other object, the moon in this case, orbiting around the Earth in uniform circular motion. That's a simplified view, however, what actually happens. What actually happens is that both the Earth and the moon are exerting forces on one another by Newton's third law, so they actually orbit each other. They orbit each other around their common center of mass, which in the case of the Earth-Moon system is referred to as the barycenter. Now they're showing the barycenter here as being outside of the Earth in the animation, just because it's easy to see, but that's actually not quite the case. The Earth is very massive compared to the Moon, so the center of mass, the barycenter of the Earth-Moon system, is actually within the Earth's interior. It's not the geometric center of the Earth, it's offset from it from a few hundred kilometers, but technically speaking, both the Earth and the Moon orbit each other in this manner. This allows us, by the way, to give us a full explanation of how the tides work. So just in a qualitative way, let me now give you that description. Okay, those of you that surf, Sean, how many tides are there in a 24-hour period? 4, that's right. There are 2 high and there are 2 low tides. So where do the tides come from? As you'll see, it's a combination of a couple of different things. It works in the following way. This is not the scale. Let's say that right here is the Earth, and here's the Earth's geometric center. Okay, and as I said, not the scale, let's say that right here is the Moon. No. Now the Earth and the Moon exert gravitational forces on one another by Newton's third law, so they technically orbit each other. They orbit a point that is in between them called the barycenter. That's the center of mass of the Earth-Moon system. As I said, they showed it outside of the Earth in the animation. That's not really the case. It's actually about right here, simplified on my diagram. The word barycenter, by the way, is spelled with 1 R. It's spelled like so. And then basically, once every 27 days, a sidereal period, each object essentially completes an orbit around the other, that is, orbiting around the barycenter. It's almost as if the Earth kind of wobbles in place. So you think of this hand here as the Moon, and this hand here is the Earth. As the objects orbit each other, they basically do something like this, like so, once every 27 days. So once every 27 days, the Moon basically traces out roughly a circle like so. Not centered at the center of the Earth, however, but centered at the center of mass. And then the Earth basically does the same. So once every 27 days, the objects are basically doing something like this, around each other, like so. Okay, now what does this have to do with the tides? Okay, well, first of all, we have the Moon exerting a force of gravity upon the Earth. But remember that gravity weakens with distance from Newtonian gravitation, gmm over r squared. So then therefore, which side of the Earth, the side closer to the Moon or the side further from the Moon, actually experiences a little bit more gravity due to the Moon itself? The side that is closer. So because there's this difference in the force of gravity on one side of the Earth as opposed to the Earth itself actually kind of gets stretched out a little bit like a football, more or less pointing towards the Moon. Now the solid crust of the Earth doesn't stretch all that much, it's essentially negligible. But the oceans, being water and fluid, can flow very easily. So basically what this means is that there's a bulge of ocean water that is pointed directly towards the Moon. I will greatly exaggerate it here on this diagram. Let me see, where's my blue? Here's blue. Like so, such that you end up with a bulge of ocean water like so, pointing towards the Moon. And if you happen to be right here, it's high tide. Now, if you go down to the beach, by the way, and somebody says that the tide is coming in, that's actually kind of a misnomer because the bulge is actually always there. It's just that when you're at your location, you are rotating into the bulge. You're rotating into the tide. Now, how much high tide you experience at any one location is going to be determined by a whole host of local variables, like the shape of the coastline, shape of the ocean floor, the ocean currents, the wind, and blah, blah, blah. That's ultimately going to determine exactly how much tide you see at any one location. But that bulge is essentially always there. So if you rotate into the bulge, that's when you experience high tide.
So if we have like a big swell, is that?
So that all of the ocean swells and so forth, like we're experiencing right now, as I said, I heard it this morning as I was getting ready for work. All of that stuff is caused by atmospheric disturbances. It's not caused by seismic disturbances. That leads to tsunami. I'll talk about that at a later date. But essentially all the ocean swells that you see, it's all basically caused by the weather and nothing else. So this is not caused by tidal stretching like was being depicted in the film Interstellar, by the way. I'll get to that later after I see the
You
film.
did watch it.
Okay, now, if this is a high tide bulge, 6 hours earlier here is low tide, 6 hours later here is also low tide. So the low tides are here and here, separated from this high tide bulge by 6 hours apiece. Okay, now, the real trick to this, however, is understanding why there is a second high tide on the other side of the Earth. This one's a little bit trickier to explain. Unfortunately, I've seen lots of marine science textbooks, marine biology or oceanography, get this wrong. They'll say that the second bulge has to do with the Earth's rotation. That's actually only partially correct. Okay, now as the Earth rotates, of course, it rotates on its axis, which then from centrifugal force causes the Earth's equator to bulge out a little bit. But that happens all the way around the Earth. So then therefore, can that second high tide be, strictly speaking, due to the Earth's rotation on its axis? No, it can't. So where does this second high tide come from? Well, it comes from centrifugal force again, but not as the Earth rotates on its axis, but as it wobbles around the barycenter. It's that rotation that causes the centrifugal force. So think of this right here as the center of a little circle, if you will, that the Earth is wobbling around. So then therefore you would experience a centrifugal force outwards from the center of this circle in this direction on my diagram to give you that second high tide. So this second high tide here is caused by centrifugal force, but not as the Earth rotates. But it's caused by centrifugal force as the Earth wobbles around the barycenter. This is a detail here that a lot of introductory textbooks in marine sciences unfortunately are very vague on, or they get wrong. As the Earth wobbles around the barycenter. That's what causes that second high tide. So this is why you get 2 high tides and 2 low tides in a 24-hour period. A couple of other interesting details here as well to briefly mention. The sun does have an effect. The sun is a lot bigger than the moon, but it's a lot further away. But it does have a gravitational effect on the tides that the Earth experiences as well, but it's only about 1/4 or so the strength of the moon's tides that is caused by the moon itself. But it does have an effect. How many of you have ever heard of the terms spring tides and neap tides? You get 2 sets of them essentially every month for the following reason. First of all, you get what are called spring tides during full moon and new moon. So let's say, for example, that this is new moon. What that would mean is that we would have the Earth, the moon, and the sun over here. The sun's gravity basically causes this bulge here to bulge outwards a little bit more like so. So you get a pronounced high tide right here on this side of the Earth. This is then referred to as a spring tide. Similarly, during full moon. Now during full moon, it would be moon, earth, sun over here. Sun's gravity causes this high tide to bulge outwards a little bit more. So once again, you get a pronounced high tide. That's referred to once again as a spring tide. This has nothing to do with the season of spring itself. I myself, I don't even know where the term comes from, but for whatever reason, it's called a spring tide. And then the other 2 tides that occur during the month that are special are called neap tides. Neap tides occur during the quarter phases of the moon, because then you basically have the sun and the moon kind of working and canceling each other out in terms of their gravitational effects. Here's kind of the idea. Let's say it's 1 1/4 phases. So you would have the moon, the earth, and the sun here. Well, the sun's gravity would cause this low tide to bulge outwards a little bit more like so. So in other words, you don't see a big difference between low tide and high tide. There's not a pronounced difference. This is referred to as a neap tide. It occurs during the quarter lunar phases. Lastly, there's another interesting detail here. As the tides are caused here on the Earth by essentially the gravitational influence of the moon, basically what that causes is a little bit of stretching or flexing deep within the Earth's interior. This then results in a generation of heat. And in part, that heat that is generated in this manner, this is one of the heat sources then which drives plate tectonics that we see here at the surface of the Earth. So in other words, some of the energy of the Earth's geology comes from this tidal flexing. One of the other interesting aspects to all of this, by the way, is through some pretty complicated effects, This actually means that the moon very slowly over time is losing orbital energy. It's losing orbital energy as heat in the Earth's interior as this tidal flexing occurs. The net effect of this is that the moon is actually receding from the Earth at a rate of a couple of centimeters per year. The reason for this is because the moon is losing orbital energy over time as some of the energy is being burned off here as heat in the Earth's interior. This is actually directly measurable. When the Apollo missions were done in the late 60s and early 70s, the astronauts actually left behind on the surface of the moon some mirrors. And every now and then we bounce lasers off of those mirrors to measure very precisely how far away the moon is. It's actually receding from the Earth at a rate of a couple of centimeters per year. When the moon first formed 4.5 billion years ago, around the same time as the Earth, it actually formed a lot closer to the Earth than it is right now. It may have only formed about 15,000 miles or so from the surface of the Earth. Imagine how big it would have been in the sky in that case. Because right now the moon is 250,000 miles away from the surface of the Earth. It's been receding away from the Earth ever since due to the tidal flexing that occurs within the Earth's interior. If you give this process enough time, by the way, the moon will actually gravitationally eventually escape from the Earth and then just become another object orbiting the sun in the solar system. It turns out, however, that the sun will actually go red giant first anyway and destroy the Earth before that happens, so it's kind of a moot point, but it is kind of interesting nonetheless.
It always stays the same. This law applies to two bodies or three or more bodies throughout.
This is called the three-body dot problem in gravitation. Three objects orbiting each other in a very complicated way. As you might guess, this is a horrible mess mathematically. But if there are no external forces on the system, notice that the sum of the three momentum vectors is always remaining the same. Yeah, you could just imagine how messy this is mathematically. And because it is a very complicated situation, now they're going to simplify things for us considerably and show us a little cartoon.
Yay!
Good ship, Newtonian.
Like so.
Nova Fleet Defender.
They do some weird stuff in these episodes now and then.
Good ship, Newtonian. Perhaps not quite the image of a Star Wars defense system. But when it comes to maintaining the physical laws of the universe, who's to say she's not up to the task? Using force when necessary. And alas, it always is. Newtonia fires an aspirator in defense of the laws of the mechanical universe. Including, of course,
think of a recoil,
conservation
however, as silly as this is. Think of a recoil as a one-dimensional explosion.
This action and reaction should not be mistaken for timidity under fire. On firing, when the Astra shell is blasted off, Newtonia recoils because the total momentum of any system remains constant.
The ship and the board.
So look at it this way. When the shell is fired, it zooms one way, and the good ship Newtonia zooms quite the other. But no matter what direction, no matter how intricate the system, and no matter its specific components, the conservation of momentum remains in play.
Now watch this. They're about to go through the proof that I did a
And
little
for that
while
matter,
ago. They do it
so
fairly
does the
quickly.
conservation of energy. That's because, although it takes many forms, energy, like momentum, is always conserved. Whether it's in the form of potential energy, U, the result of doing work, W, or changing to kinetic energy, K. Or dissipating into yet another form, heat, or Q.
Sometimes we use the very...
All energy is conserved, strictly and absolutely. Again, whatever form it takes, energy, like momentum, is always conserved.
Now watch
Of course,
this.
the conservation of energy rules every game, no matter what form of energy is involved, and no matter what the masses of the bodies are. But in this game, there's only kinetic energy. and all bodies have the same mass. What happens when they collide? Momentum, P, is a vector quantity that's the product of the mass of an object times its velocity. In other words, the velocity is equal to the momentum divided by the mass.
Here's kinetic energy.
Kinetic energy, K, is 1/2 mass times velocity squared.
Now here's this alternate way of writing kinetic energy. P squared over 2r.
Therefore, kinetic energy is P squared over 2m. All of this reveals one of the great secrets, not only of nature, but of how to play winning billiards. When one ball with momentum, P0, strikes another which is at rest, there are only two possible results. After the interaction, each ball has some momentum, P1 and P2. According to the law of conservation of momentum, P0, the initial momentum, is equal to the final momentum, P1 plus P2. This is a vector equation. The three vectors form a triangle, and in this case, a very special triangle. Remember, in the collision between billiard balls, the only form of energy involved is kinetic energy, ignoring a tiny bit of heat generated by the collision. Not only is momentum conserved, but also kinetic energy is conserved. Since the masses are the same, P0 squared equals P1 squared plus P2 squared. But that's the Pythagorean theorem for right triangles. And as a result, P1 is perpendicular to P2. In other words, when one billiard ball strikes another, which is at rest, they come off at right angles. That's one possible result.
Okay, so now watch the right angles in these shots. Don't swell. Very nice right there, good cut. Okay, this guy forgot, however. This guy didn't.
But is that the only possible outcome? No. A clever player can make things happen by applying English. In other words, by making the ball spin as well as roll. But even without English, there's still one more possibility.
The head-on collision.
One more way to make a shot that won't work if the balls come off at right angles.
It's just a matter of geometry.
If the balls hit just right, that is exactly head-on, both laws, conservation of momentum and energy, can still be satisfied in another way. One ball can stop completely and give all of its motion to the other one. That's the second possibility. This was exactly what René Descartes meant. One ball gives its motion to the other. The total quantity of motion on the universe has been conserved.
I'm going to stop the film there. We're kind of getting towards the end of the period. I'm going to collect from you next time at the beginning of the period the notes that you took from today's film. And then I remind you about the web assign once again. Remember that last week, because we had Monday off, I put off in part the last week's web assign for this week. That's this way.